You think you just show up, huh? Whenever you want?
Yeah.
That doesn't mean anything.
That's ridiculous.
Didn't I show you this picture of this house in DC? I don't know why.
How goes it?
I think it's better how much it's
Awful.
before, and I was
Horrible.
like-
Okay.
I was like,
That's unfortunate.
This sounds unfortunate.
because I knew it was in DC.
All right. Questions about anything before we get going?
1.8.
Are we doing 27.1 pound stuff today?
No.
We're doing more stuff with moment generating functions, and we're going to talk about
I meant to study those before I can pass.
how different combinations of different types of random variables and what random variables you get from them.
Okay, Dr. I've got a quiz for you. Don't look at anything. All right, close your book. Real quick. You can mark your page, but close your book. Okay, you got it. You got it. I've got a quiz for you. All right, on your thing, you have to name or write down all the ones you've done. You gotta see if you know them.
Why you go on the lake?
Because I want to see if you know them.
Why are you testing me? I took the test.
Because Dr. Joe, do you know them?
Yes.
Yep. Ready?
No, we're learning new stuff. Which is why we're going to go, and I'm not going to write down all this longer.
If you go about 10 minutes outside the cater anyway, yeah, you're fine. I found some really nice ones. There's actually some nice houses that I should consider part of the game.
There's Monticello's really nice. Really cheap.
Because like they're kind of small outside.
I was trying to clean out stuff out of my office.
Champagne's the best place to go.
There we go. All right. All right. So last time we talked about moment generating function stuff, right? No. I'm going to write down some moment generating functions anyway, Grace. So.
I was going to quiz you on all of them, but.
All right. So.
Yeah, hers is better, I agree.
Well, stop. They're in my desk in my apartment.
I have a picture of them.
Contrary to about half everybody's in there.
All right. So if the x1 out to xn are independent, and if your y is the sum of, say, c sub I times x sub I, then what does your moment generating function for a y look like?
Did we do this yesterday?
Yes. We did it for, I think, for 2 variables, but it extends. When you add random variables together that are independent, what do you do with the moment generating functions? Multiply them. When you've got the constant multiple, where does the constant go? Not out in front. It goes inside the function here, multiplied by the t, right? So this will be the product of your moment generating functions for the x's, where you'll replace the t's with c times t.
So is C your constant?
C is the constant, yes.
Is C changing? Is that why there's not?
Yes, it could be different numbers. All right, so
What's the balance for the?
it's the same as, it'd be I equals 1 to n. It's the same as in sum. I just didn't feel like writing the notation in there. All right, so as an example here, let's say x1 is Poisson with lambda 1 equal 3, and x2 is also Poisson with, let's say lambda 2 equals 5. And I ask you to find the moment generating function of y, where y is, let's say, how about 2x1 plus 4x2. Pardon. So, according to the theorem that we wrote down, the first thing we need to know are the moment generating functions for x1 and x2. Right? So what is the moment generating function for x1? Okay. Good. Because it's e to the lambda times e to the t minus 1 up in the exponent. And what would be your moment generating function then for x2? Okay, good. All right, so now when we do the moment generating for function for y, we're adding these two things together, but we've got multiples for the x1 and the x2. So what do we do with the multiples here? Put it in with the t, right? So this will be e to the 3 times e to the 2t minus 1, right? And then multiplied by e to the 5 times e to the 4t. Minus 1. And then you could simplify that if you'd like, but that would be what your moment generating function would be in this case.
You would take that as an answer.
Yeah, that'd be fine. You don't need to simplify it.
Cool.
That would be what that one is at that point. Does that make sense? Okay. All right. So what we're interested in with this particular theorem, besides doing little things like this, is what happens when we take sums of distributions of certain types. What kind of distribution do we get? So let's say in this case I didn't have the 2 and the 4 in front of the x1 and the x2. Okay, I just had y was x1 plus x2. So I'm adding two Poisson distributions together. Okay, so if I did that in this case, I'll call it z is x1 plus x2. The only thing that would change here would be what? What would I get rid of? The 2 and the 4 up in that exponent, right? Up in the exponent for the e. So I would have e to the 3 times e to the t minus 1 and e to the 5 times e to the t minus 1. Now this one I am going to simplify. What would you do with the exponents? Add them. So what do you end up with? Yeah, so it'd just be 8 times e to the t minus 1. Yeah, right? Okay? Because I can just treat the e to the t minus 1 as a single term. All right, so now I look at this moment generating function and ask, what is that? What kind of distribution is that the moment generating function for? It's a Poisson. What's the mean? What's the lambda? 8. So what we just showed here for this specific example, but it's going to work in general, is what? When I take the sum of independent Poissons, what kind of distribution do you get? A Poisson. Right? And so that'll work for any Poisson. And what do you do with the means when you add them together? Add them, right? Also turns out, what will you do with the variances when you add them together? Well, you'll also add them, right? Okay? All right. Yeah.
Does that apply to like all Poisson?
Well, we're going to do some other ones. Okay? So... So let's let x1, x2 out to, say, x, I'm going to change it to an r, x sub r, be independent and identically distributed geometric random variables with, I'll just say parameter p. We need to know what the probability of success is for geometric, right? We agree? Okay. So I need to know what the probability of success is for geometric, which is why I just said call the parameter p. And now let's let y be your x1 plus x2 out to x sub r. what will the moment generating function for y be? Well, what do I need to know? Yeah, you need to know the moment generating function for each of the x's, right? But what are we assuming about each x? Yeah, they're identically distributed. They're all geometric, right? So if I do the moment generating function for a single x of I, what's that going to be?
It's gonna be.
It's going to be.
Oh, you got it. It's all you, man.
We're doing geometric though with the p's.
P e to the t over 1 minus 1 e to the t 1 minus p.
Oh, okay. I was gonna let him do it, but yeah, you got it.
P e to the t over what was it again?
1 minus e to the t.
E to the t.
Times 1 minus.
That one? Is that what you're telling me?
Dr. Jones, did you not know that?
What do you think?
You didn't know it.
It says pet. I know.
It's the pet one.
Yeah, I agree. This is okay. All right. So what are we going to do with each of these moment generating functions? You're good, Nate. What are we going to do with these moment generating functions?
Add them. No, multiply.
We're going to multiply them all together, right? And they're all identical. So if I multiply them all together, what power is it going to get raised to? The r. The r is the number of variables.
Oh, I used N. That's fine.
I only used r because I want to make a point.
Okay, whatever floats your boat.
Our note is supposed to be different today.
I do want to be different today. Do you recognize this as the moment generating function of anything?
Yeah,
Negative binomial.
Hey, it does look like negative binomial, doesn't it? Right? So what does that tell you that the sum of independent and identically distributed geometric random variables gives you? Turns into a negative binomial. Now this is the point of doing this with the moment generating functions, is so we can recognize the function from that particular standpoint. All right, we can the distribution from that particular standpoint, right? Putting those moment generating functions together, making a new one, hey, I see the new distribution out of this. So far we've got sums of independent Poissons as Poisson, okay? We've got sums of independent and identically distributed geometrics is negative binomial.
Let's do exponential.
Okay, well let's do exponential. That sounds like a good next one to do.
Did we do exponential yesterday? Or the other day?
Do I do sum of exponential?
Is it the same thing? Is it just another exponential?
Let's say we do x1, x2 up to x of alpha.
We're gonna get a chai.
Only if you go to a coffee shop.
Are the means added together for that geometric function?
Yes, the means will be added together, yep. Because it's r over p in that case. All right. So let's say we have independent and identically distributed exponential variables with parameter theta. And let's let y be the sum of these. What's wrong? What'd you say?
Said your coins are fast. I'm just
I'm writing the exact same thing over again. I'm just changing geometric to exponential.
well, right, just to prove my point. I'm currently writing identically distributed. Well, I was summarizing what we did in the last one, so that I know for later.
IID. There's two IID.
Yeah.
It's too hard. I'm already past it now.
I. All right, we ready to talk about this one now? Or is Grace not done writing?
Oh, you can go ahead.
Okay. Moment generating function for y. All right, well, what's the moment generating function for each x sub I?
1 over 1 minus
1 over 1 minus theta t. So what, and now that I've got y is the sum of the x1 out to x sub alpha. I know in this case, the alpha actually is an integer, but again, using the different letter to illustrate a point. What do I do with all these moment generating functions? Multiply them. So what are we going to get for the moment generating function for y?
1 over 1 minus theta t.
Yeah. Right. So we notice that this 1 over 1 minus theta t to the alpha is the moment generating function for a gamma. So if you sum up independent and identically distributed exponential random variables, you get a gamma with the same theta and then how many other things are in your sum. Yeah?
So Poisson, the only one that's Poisson.
Yeah, Poisson, no, there's another one that stays the same. We'll get to it in a minute. Actually, there's two of them that stay the same that we'll talk about. One of them is the one I'm going to write down now. And the last one's actually the distribution we'll focus on for the rest of the semester. This one's gamma, yep.
Is that next one going to be chi?
Yeah, I'm going to talk about chi, yes. Chi squared.
Are these means added together?
Yes. I mean, anytime you have the sum of random variables, the means are always added together.
I'm gonna get that. No, I don't have that.
Special reason why Poisson distribution. We'll try to get this. We just name whatever we want.
With the sums of the things, you mean?
Yeah.
Where it stays the same?
Yeah.
The idea behind it is that if you think about the Poisson as being how many occur per unit time, when you add them together, it just added how many things should occur per unit time. Versus exponential, it's waiting time until the first occurrence. Well, if you add them together, now you're getting waiting times for several occurrences. So that's what the difference is between them. And the same thing with geometric. A geometric is number of trials until first success. If you add them together, you get number of trials until you get to that many variables. All right. So let's say we do chi squared. Let's say we let x1, x2 out to x of n be chi squared random variables. Let's say independent chi squared random variables. I said chi. It's not chi by any stretch of the imagination. Could be chi.
I'm going to tell everyone from now on that I talk to this chi.
Okay.
Not letting them bother.
They're gonna make it pronounce this way. They're gonna make Marshall pronounce it Lubital, right?
I've given up on Marshall. I've given up on Marshall pronouncing it right.
Oh.
I've heard him say El Hospital or whatever whatever you say.
I've said it a lot of different ways.
I know.
I just get so excited every time I get to use it.
El Hospital. El Hospital. All right, so we've got x1 to xn are independent chi-squared random variables. This one I'm going to allow the degrees of freedom to change as we go along. What will your moment generating function look like for a particular I? Okay, so in this case it would be r sub I over 2, right? Just using the I as the subscript to be r sub I over 2 if I'm doing the one for x sub I. In the previous ones, we've had the same parameter. In the previous two, we've had the same parameter, which is why I didn't have an I sub I in it. Yeah, Morgan?
So is that why you didn't put
That's why I didn't include the identicalness in this case, yeah. All right, so let's let our y be the sum of these again. Then what's your moment generating function for y going to look like? Well, I've got n of them, right? But they've got all different exponents here, right? So I've got to multiply them all together. That's why we had exponents before. They were all the same, but they're different in this case. If we multiply them all together, what's going to happen with all your exponents down here? You're going to add them, right? When you multiply them all together. Okay? So this will turn into 1 over 1 minus 2t to the sum of the r sub i's over 2. Because you're going to add all the exponents together. What is that the distribution for? Okay, that is a chi-squared. How do I know it's chi-squared? Okay, so my 2 is my theta, right, from the gamma distribution. And the exponent is an integer over 2. It can be written as an integer over 2, right? So I recognize this is a chi-squared. How many degrees of freedom does it have? The sum of the r sub i's. So what happens to independent chi-squareds when you add them together? It stays chi-squared and you add the degrees of freedom. Yes, Grace. Every time. Because when I do the expected value of the sum, it's the sum of the expected values. It has nothing to do with distributions or their independence. That's the property of expected value. Are you going to ask me for the next one too? Okay, cool.
What did you say? You get a chi-square distribution. What is the degrees of freedom changing?
Yep, it's this degrees of freedom here. So when you add independent chi-squareds, you still get a chi-squared and you add the degrees of freedom. All right, last one that we're going to do, and it's the most important one, so it's the one we're going to play with after we get done with it. Let's let x1, x2, out to xn be independent normal variables with means u sub I and variances sigma sub I squared. What does the moment generating function look like for an individual x sub I in this case?
Sigma squared over 2.
Thank you. That's what our moment generating function looks like for each of them. Okay, so if your y is the sum of the x sub i's again, how do we find the moment generating function? Oops. How do you find the moment generating function for y? Yeah, multiply them all together. If we're going to multiply all the ones together of this form, what do you do with the exponents? Sum them, right? And then I can add like terms. So what are we going to sum here? The mu's, and here will sum the sigmas, right? So what do you do with the means, Grace?
Yeah.
Good. So we get e to the sum of the mu sub i's times t, oops, it's up in the exponent, plus the sum of the sigma sub i's squareds over 2 times the t squareds. So this is still normal with the mean, the sum of the mu sub i's, and the variance, the sum of the sigma sub i's. Okay? Bless you. All right. What if I put some constants in front of the x's? What if I put a c in front of this x1? Well, then there would have been a c here, right? In front of one of the u sub 1. There would have been a c squared here, right? Because I have a c for the ct. I put a c in for the t here. I put a c in for the t here for that one. It would square it, right? So we notice that we would multiply the variance in that particular one by the square of the constant. We've talked about that before, right? When you do the variance of a times x, it's a squared times the variance of x. Same idea here pops out when you do this with, for the moment generating functions. It's just that, notice that the constants won't change whether or not it's normal. Right? So if you do a sum of normals, even if you have constant multiples, and if you have linear algebra, we refer to that as a linear combination of the random variables, right? When you do sums of constant multiples, it's linear combination, right? Use those words before you've seen linear, right? If you do a linear combination of normal random variables, you still get a normal random variable. Okay? And it changes the mean by the same constants, and then you would do the sum of the squares of the constants for the others. The variance. All right, so why do I care? Yes.
Are all the variances added up for all the other ones too?
Yes. Because if they're independent, then the variances get added. We don't have to worry about covariance in that case. All right, so let's do an example here. Let's
You
say...
didn't answer why you cared about it first.
What's that?
You didn't answer why you cared about it.
Why I care about what? This?
Yeah, you said, why do I care?
Why do I care? Well, I'm going to do an example. All right. Let's suppose that x is normal on, let's say the mean is 3 and the variance is 16, and y is normal, mean is 5 and the variance is, let's say, 49. And then further, let's suppose that x and y are independent. And I ask you to find the probability that, let's say, x plus 2y is less than 10. Let's do it. All right. X and y are independent normal random variables. So what do I know about x plus 2y? What kind of variable is it going to be? Normal, right? As soon as I know that x and y are normal, actually it doesn't matter if they're independent or not in that case. As soon as x and y are normal, linear combinations of x and y are automatically normal. Okay? So just to write that down. So since x and y are normal, x plus 2y is also normal. Let me give it a name. What name do you want to give this variable? Just want to write x plus 2y every time.
B.
I don't want to use z because I use z for the standard normal. I want to use a w. Pretzel. Oh, pretzel. Ooh, I like pretzel. Let's see if I can do a pretzel. Maybe I can't do a pretzel. I can think about what a pretzel looks like.
It'd be like a heart with a peace sign.
Oh, wow, I can't do a pretzel.
It's a sideways pretzel. Oh, you had a sideways pretzel?
I had a sideways pretzel? How do you do a pretzel?
So go from there.
Go this way. And then what do I need to do from here?
Are you
And then
trying to do sideways one?
I do something like that, don't I? Oh, that's really ugly. Wow. I'm going to go back to W.
No. Ready? No, guys, no. Can we show you how to do it?
You want to do that? You want to draw a pretzel?
I'll do it back here. Okay, I'm trying to.
Dr. Olson tried to draw pretzel last year.
How much?
A lot of trouble with it. It's really good. Should
Oh, wait a minute.
pictures today.
Who did? I forgot what I did. Dr. Joe, what did you do?
This is
I think
really
I-
not right.
Grace.
This is
Yeah.
Go like this. Like start and go up, and then come around and make it cross over.
Start, go up.
No. Go
Like
the other
that.
way.
No,
Wow.
There we go. Took me a while to think about how that didn't look.
That's
I was like, roll line.
Woo!
All right. What's the mean of W?
8.
It's not 8.
Oh, I lied.
It's 13, right?
Because you add the means to that.
It was x plus 2y, right?
Oh, I was like 3 plus 5. I swear it's 8.
It's 3 plus 2 times 5, right? What's the variance of W? What's the variance of x? The variance, 16. What's the variance of y?
90.
What?
2 times.
49. What do I have to multiply the variance by since it's 2y? You're going to multiply by 4, right?
That's
Because I got to square the constant, right?
That's 212.
really tough there.
There's a lot of hard math there. Everybody see where I'm getting those numbers?
Yes. Okay, so we're putting a 4 there because we have to square.
We have to square the 2, right. It kind of sucks that I have to square the 2.
Because I'm not, it sucks.
Why do you have such strong feelings on whether or not I have to square a 2?
Because
No,
the 2
it
is a
sucks.
2.
No, it sucks because I'm not going to remember. Like, 2 squared is 4. That's not hard. But remembering that the 2 is squared.
I have different feelings about this. 2 is an independent person, and 2 should have to be a 4.
It's good.
Well, I got that, but I'm not going to remember.
All right. So with the probability that x plus 2y is less than 10, or the probability that w is less than 10. We know it's normal. We now know that the mean is 13, the variance is 2. By the way, what property am I using of the random variables in this particular case that I can just add these variances together and not have an extra piece on the end? What are we assuming about x and y?
They're independent.
The covariance is 0. They're independent, right? If they have covariance, I would have to do a different thing.
Wait, we're assuming they're independent?
Yeah, we're assuming they're independent. If they're not,
Then we have a lot of like issues.
well, then you have to go back and remember what we talked about with the bivariate normal. That was with the bivariate normal. Remember, you had if you have covariance, if you have correlation, then your mean of your y is what? You remember?
Wait, what was the question? I missed it.
If you've got correlation between your x and y, what is the mean for y then? That's what you have to do. So the mean for the y is if they're if you do
Row.
well, there's a row in it. Yeah, you have the row and the sigma sub y over sigma sub x.
Oh!
Remember those? Remember you had the least squares part,
Oh, if you would have just said what's the least squares line, I would have been like, boom, right there.
right? You have this part, right?
Yeah.
So if you want them, what I was doing was I need the expected value of y given x, right?
Mm-hmm.
Is the mean of the y, right? Plus row y, sigma y over sigma x minus the use of x, whatever the x is. Right, remember that?
Yeah.
Okay, and what's your variance for the y given x?
That was.
Row
Row your boat.
You both
At this point, yeah.
The correlation.
downstream.
Yeah, that was familiar.
That look familiar?
Yep. I feel like I should have wrote it down.
So remember, they have correlation. You have a little bit of things that you have to worry about with the expected value and the variance. These are independent.
Are we trying to find that?
No. No. I was trying to remind.
That's if we didn't assume.
If we didn't assume their independence, then you'd have issues.
Okay, well, we're
Okay.
assuming independence, so it's fine.
Yes.
And we are assuming they're independent because it says so.
Because it says so in the problem. Yes.
Oh, I didn't write that down. That's why I was really confused.
Yeah. All right. Anyway, I know this is normal. I know it's mean. I know it's variance. So how do I handle a probability problem like this? What do I need to do?
You gotta subtract the mean and divide by
I got to subtract the mean
standard deviation.
and divide by the standard deviation, right? And this is why I didn't want to use z, because z is our standard normal, right? We're doing a z-score essentially, correct?
Yeah. Love these parts.
Table.
Dr. Joe, I don't have my table.
You don't have your table? You need a table? Is that what you're telling me? I think I can help. I think I can help you out. What was the number?
I got 0.5832. One minus that.
0.5832.
Wait, no, one minus that.
What?
Oh, I might have done it wrong, Dr. Joe.
I got
Everybody's saying
zero,
what?
negative 0.206.
How'd you get a negative?
It was 10 minus 13.
Oh, you're talking about for the z-score?
Yeah.
Oh, I was talking about for the percent.
Oh.
Yeah, then you do 1 minus.
Yeah, I did.
Okay, what was the z-score?
Negative 0.206.
So I'm looking for this value here in the table.
Wait.
What? I got to subtract. I got to do 10 minus 13.
0.206.
Oh, 206. So 0.21. That number. 13.
Minus 13.
So you get negative
Divided
3.
by
0.5832? Is that what you were telling me?
One minus.
Okay. All right, so go back over to my thing here. Somewhere. Wherever I was. Where was I?
Untitled.
All right, so this is phi of negative 0.21. So that's 1 minus phi of 0.21. 5832. So notice what I did if they were independent, right? Just figured out the mean and the variance of the new random variable that we've got is the combination of the two. Know that it's normal, and then just attack the problem like we did before. Does that make sense? What do you need? What do you need, Megan? This way? Sorry. Go back and forth. It won't go in circles, though, unfortunately. I can go that way, or I can do that.
You gotta do it really fast so it appears.
Yeah, I wasn't doing it right. That okay? All right. All right, so what if we wanted to know, let's suppose that our y, instead of being the sum of the x of i's, let's say it's the mean of the x of i's. This is a different thing. I mean, I'm going to go back to normal distribution here at the end, but what if we had the mean? So we use x bar to denote the mean. When the way we do the mean, of course, is we add the x's together and divide by n. I'm going to assume that, I don't need to assume that the x's are independent for the first part, but assuming the x of i's are independent, what is the mean for y going to be here? I need independence for the variance, so I don't need it for... So I'll write mu sub x bar. What will the mean be? What will the expected value be? How do I find expected value of a sum?
Something that I should know, but I don't. You multiply the sum by 1.
Making it way harder than you need to here. What do you do with, what does expected value do over sums? It's a sum of them, right? What do I do with a constant? Pull it out in front, right? So this will just be 1 over n times the sum of the expected values. Let me just write it this way. Expected value of x1, expected value of x2, expected value of xn, right? Remember doing these? Oh, yeah. I also meant to write in here, though, let's suppose that they're identically distributed. So let me write that in. Let me write that in here now. If they're identically distributed, what can I say about each of those expected values? They're all the same, right? So I might as well say that this is 1 over n times mu sub x, whichever x it is, right? What happens to your n's? They cancel. All right, we'll do the variance here in a second, but the idea behind this is the following. Remember, when I write these x sub i's down like this, I want you to think random sample. Okay? You've got some distribution, and I've taken the sample from the distribution, and right now I'm taking the mean. If I do this over and over and over again and do the mean of the means, that should give me the same thing as the mean of the individual pieces. Right, so the mean of the sample means is the same as the mean of the entire distribution. That's what that says. Okay? Kind of makes sense, right? If you're going to take samples and average them, and then average the averages, I should get the same thing as the average of the whole leg. If I do this over and over and over and over and over again, right? Okay. So that's not a huge surprise that should turn out to be that way. Well, let's look at the variances now. So again, we're going to assume that they're independent and identically distributed. If I want the variance of y, or the variance of x bar, what happens when we do variances when I have this 1 over n that's out front? What do you do with the constant when you've got variance? Square it, right? So you have 1 over n squared times the variance of x1, variance of x2, and so on to variance of xn. Right? And again, if they're identically distributed, these are all the same thing, aren't they? So this will be 1 over n squared times n times the variance of just an x. Because there's n of them. Each of them are the same. So we get the variance of the x over n. Okay, so what does this mean in general? We just said that if we do the sample means and look at the expected value of the sample means, it doesn't change, right? But what happens to the variance? Does it get bigger? Does it get smaller? Does it stay the same? It's smaller, right? And the bigger the sample size gets, the smaller the variance gets. They use this idea to detect cheating in standardized testing, by the way. The larger sample you get, the less variance in the mean you should get. All right? So if you've got a school where they've got a mean that's way up above everybody else's, they go investigate it more because it'd be very, very rare to have that happen. Right? If you say you had a mean, the mean's usually 20, and an individual person gets a 25, well, that's not that rare, right? Even with a standard deviation of 3, that's not a very rare occurrence, right? But if you take 50 people and the mean turns out to be 5, or it means 25, if your variance was even 5 to start with, divide it by 50, now your variance is only 10. Right? The chances that a whole sample of 50 had that high of a mean is very, very small. So there's a movie called Stand to Deliver where about a teacher that was teaching AP Calculus in inner city Los Angeles, a very, very poor, underperforming high school. And he got all these students to do all well on the AP test, so they accused him of cheating because they'd never done that historically, and it was out of the norm. Moral of the story was they had the students retake the test, they all did well, they got their scores reinstated. It was fine. I mean, that's the point of the movie. But the idea was that they used this concept of the fact that when you do samples, the variance goes down. And this was so far outside of what should have happened if it were random chance that they questioned it and they said, oh, they picked a cheater.
So just to clarify, you've seen that movie?
Yeah.
So out of all the movies, you've watched 10 in the last 10 years. That
Probably.
was one of them.
No, I watched that like 15 or 20 years ago.
Have you seen that movie about that mathematician guy, like Jon Snow, who goes crazy?
No, I haven't. Now, I watched Good Will Hunting several years ago, and it was awful. God, I hated that movie. I don't know why everybody thought it was such a great movie.
Why don't you like the movie?
I just...
Joe, that makes me so sad.
Joe, you would like Monty Python.
I've seen Holy Grail and Life of Brian. That's
Did
been...
you like them? Were they funny?
Yeah, they were funny, but that was like 30 years ago. I'm old. I thought it was like 30 years ago. I have not seen Frozen 2 yet.
Have you seen Frozen 1?
I have seen, well, I have 3 nieces. I mean, my number of movies probably has popped up a little bit because I've seen Disney movies. So.
But those aren't.
All right. That's it? What?
Disney movies aren't movies. Kind of rude.
You
All right.
haven't seen the Marvel movies. Can we talk about that?
I saw Wonder Woman.
So Disney is actually considered Star Wars and Marvel. So you
Okay.
You probably got the stuff too. Yeah. $1 billion.
All right, so we're going to continue this concept Wednesday and do the last thing that we're going to talk about this semester about the central limit theorem. And the idea behind the central limit theorem is about samples. The idea is that no matter what the distribution is, if your sample size is big enough, the distribution your sample means is normal, essentially. That's the idea. So that's why the normal distribution is so important, because essentially everything is normal.
Did they like set a number up there? Wasn't it like 500 or something?
Well, 30.
N equals 30.
I don't.
Yeah.
I thought
Tonight, tomorrow, and Thursday.
I think we did this in AP Cal in high school.
Did I
Not Cal, not AP Cal. AP
Stats?
I thought it. I know I did Thursday. For sure.
Dr. Joe, would you be fine with me taking it at night? Or would you have to be here for me to take the final?
I probably need you to be here for me to start it.
Okay.